Um, let's go to questions from the homework or anything like that. Any questions from any homework assignments you might have tried yet? No? You guys didn't go on there and just go crazy with probability last night? On which problem? On what? First one? 26? Does this look right? Who asked the question? I couldn't even tell. Oh, okay, I'm reading. So, this is a standard deck of cards with 52 cards. One card is selected from the deck. The probability of randomly selecting a 7 or a 2. Which one was it, all of them or just a particular one that got you?
I think it was just
The selecting a 7 or a 2 or a queen. So for probabilities, we're going to go with the basic definition of probability says we just need to do the number of possibilities divided by the outcomes. So here we got 52 cards, and it wants to know the probability of this one was, so like B, for example, was 7 or 2 or queen. So 7 or 2 or queen. Now, are these are 7s and 2s and queens all mutually exclusive? They have to be. Why?
because you can't have
Yes.
both at the same card.
Right. Yeah, they can't happen at the same time. So in this case, we can just do we can just do 7 plus 2 plus queen, or we can just add them all up together. So we don't have to worry about any overlap. So I think there's 4 7s and 4 2s and 4 queens out of the 52 cards. So I think your probability is going to be 12 out of 52. And I'm assuming they would just want a decimal representation of that. Yeah, round your probabilities to 3 decimals. So whatever 12 out of 52 comes out to be, I'm not really sure. Do you understand where the 12 comes from, though?
Also, on number C, on it,
On C.
how many 5s are there?
Oh, so now C is one of those examples where there is some overlap. So like yours might said 5, or did you say it's 5 or diamonds or something? Or
Yeah, it says,
yeah, so that's a little bit different scenario because if you're looking at probability of 5 or a diamond, 5s and diamonds overlap, right? There's actually one 5 that's also a diamond. So what you have to think about here is that this is you have all the diamonds, so your ace of diamond, your 2 of diamonds, 3, 4, your 5 of diamonds, and then the rest of the diamonds up to the king of diamonds, right? So that's 13 cards. But then we also have to tack on, but there's only 3 other 5s left, right? Because there's the 5 of clubs, the 5 of spades, and the 5 of whatever I missed. Hearts? Yeah. Because one of those 5s is already taken up inside the hearts. So there's only 3 more to tack on. Does that make sense?
yeah.
Yeah, so there is some overlap we have to consider there. So it looks like in this case it would just be 16 out of 52, and whatever that came out to be. You have to subtract the overlap. Okay, yeah.
So on the first one, you know how you didn't have to like actually go through
Mm-hmm.
and write every single scenario down?
Mm-hmm.
Is that just because they didn't overlap?
Right, because
So on the bottom line, you have to write every single one down?
no, not necessarily, because if we're just doing the formulas here, you know, the first one was 7 or 2 or queen, right? But all 3 of these events we decided were mutually exclusive. And so technically the property I was using here is when they're mutually exclusive, you can just add their probabilities together. Right? So 7, probability of 7, there's 4 out of 52. Probability of 2, there's 4 of those out of 52. Probability of queens, there's 4 of those out of 52. Technically, this other one, I don't have to necessarily list out events. I could use our formula. So the probability of 5 or diamonds it should be the probability of 5 plus the probability of a diamond minus the probability of 5 and diamond. That's the general addition formula we learned yesterday. So if you think about that, the probability of a 5, well, there's 4 out of 52 of those, right? The probability of diamonds, well, there's 13 out of 52 of those. But how many cards are a 5 and a diamond? 1. So we would subtract out the 1 out of 52 that is a 5 and a diamond. And you'll get the same answer because this is going to be 17 minus 1 would be 16 out of 52. So you don't necessarily have to list all the outcomes.
Like on the test, we don't have to.
No. I don't think so. Yeah. Good question. Any other questions about that? Okay. Cool. I made another activity. It's an easy one. You guys get to go roll some dice for me. So this is what I want you to do. I want you to go find a six-sided die. So I'm assuming somewhere in your house or the house of someone you know, you can track down a six-sided die in a game of Yahtzee or Monopoly or something like that. Yeah. Anybody think they'll be unable to locate a six-sided die?
Can I do it with a D20?
Sure. You may do it with a 20-sided die. It'll change the problem a little bit, but you're still very possible. So most of us will be using six-sided dice, but that's okay if you use a different number. Just make sure it's fair, right? If you want to use a four-sided dice or I don't know, whatever. Just make sure it's fair. At least 6 sides. So I'm interested in 2 things. I want to know when it's going to land on the number 2. I also want to know when it's going to land on a multiple of 3. So obviously you could do this for a bigger die because you just have more multiples of 3 basically. So what I want you to do is I want you to roll it a couple times, and I want you to start observing how often each of the events occurs. So for example, when you roll it 5 times, I want you to record how many times you get a 2 and how many times you get a multiple of 3. Right? Easy enough. And then after you roll it 10 times, I want you to record again. And 25 times and 50 times and 75 and 100, right? Now you don't have to do 100 original rolls after your 75. You can just do 25 more, right? And just tack the totals on. I mean, you can recreate them if you want. It's not like it would take you that long to roll it, right? That many times. Okay, so figure out how many times the 2 pops up, how many times the 3 pops up, and then calculate the proportion. So what was the proportion of 2s out of 5 rolls? So that would be, so if you were doing, does my pen work on Microsoft? Oh, it does. Hey, look at that. It works on Word too. So like say here, you rolled it and you got, 2 2s. Your proportion would be 2/5, 0.4 or whatever, right? And so and then maybe you roll it 10 times and you get 3 2s out of that, so your proportion is 3/10, which is 0.3 or something. Okay? And so just go down the line here and fill all those in. And do the same thing for multiples of 3, and I want you to fill those proportions in. Okay? Then what I'd like you to do is make a plot. So for 2s and then for multiples of 3, what I'd like you to do is make a plot where here, here's your number of rolls. So it'll start at 5, 10, up to 100. And then here's your proportion. So proportions are always between 0 and 1, right? So then plot, maybe 5, it was at 0.4, your 0.5. And then it's going to go maybe was at 0.3 or whatever. Anyways, I want you to plot the proportion as a function of, a little scatter plot. Does that make sense? Yeah. And do the same thing for multiples of 3 in proportion between 0 and 1. And go ahead and plot that for me, okay? And then answer a couple questions. That's all. I don't think it'll take you more than 15 minutes. It's pretty easy. But, yeah.
Is there a way we can do that on the computer?
No.
No?
Oh, the plot?
Yeah.
Sure. 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 If you want to do it on the computer, you would just enter you would just enter it as a, you would just enter plotted points. So like this would be your x variable and this would be your y variable, you know? So, because we want our numbers going on the x-axis and our proportions going on the y. So you could just enter a column of the numbers on StatCrunch, and then you could, the next column, you could enter all your proportions of 2's, and then you could do a scatter plot. And it'll pull that up for you. Sure. I thought you meant could you roll the dice on the computer.
Oh no.
Technically you can. There's some simulators on there, but I'd like you to do, I'd rather you do it by hand, because that's way more exciting. Okay. Cool. Any questions about that? Bring it back next week? Yeah, it won't take that long. I think I put on there Wednesday, but you probably could do it in 15 minutes today or over the weekend too. All right, just try it. I just want to see what happens. Actually, I want you to see what happens. I think I know what's going to happen. But I've been wrong before. Trust me. Many times. Okay, so if we don't have questions, I'm going to move on. You guys ready to move on? Let's do it. So we talked about a lot of other concepts in probability. Started coming up with some formulas. We looked at complements. This was the addition rule we were just referring to. And yeah, just basically messing around with probability. The last thing we touched on was conditional probability, right? Where we were looking at the probability of an event given another one. So we came up with a formula for that as well. And we used it to check against the solutions of that problem with the teachers and the field trips. Okay, so I think was that the last thing we did? Yeah, that was. All right. So let's start out here with another example. So 5.1% of property crimes are committed in rural areas of the U.S., and 1.6% of all property crimes are burglaries in rural areas. So what percent of property crimes in rural areas are burglaries? So, what do you think? How could we set this one up? What's the two variables we got going on here? Yeah, so there's two things going on. We got this idea that maybe we'll call it P. P is a bad one, because P is our probability notation. Let's not use P. We'll just use A's and B's. So let's call A is the event that something is a property crime. Okay. So there's different types of property crimes, I imagine. Burglaries are one. I suppose another one would be maybe vandalism, or I don't know. Anyways, so then you also have these other types of crime, which are burglaries. Okay. So one of the steps I usually do when I'm trying to solve probabilities is I like to give events those letters so that we can somehow, my goal is to somehow morph this into a formula that we can use, right? So just like in algebra, your first step for solving word problems is assigning variables. I do the same thing for these. The next thing I want to do is figure out, okay, what are we actually trying to solve for? What are we actually trying to solve for here?
Percent of crimes in rural areas are burglaries.
So we're trying to say what percent are property crimes that are burglaries. Okay. So, I guess technically it's burglaries in rural areas. This is hard to say. Burglaries in rural areas. Rural. Okay. Okay. So what do you think? What percent of property crimes in rural areas are burglaries? Wait, is that what I want to know? I think it's burglaries is not in rural areas. This is property crimes are in rural areas. If I had to say that word much longer, I'm just gonna give up. So what's the actual unknown? How do you write the unknown as like a probability statement? Boom. This is what we're trying to get, right?
You want A and B, right, together?
Yeah, it looks like what we're interested in is what's the percent that are both, right? A property crime in a rural area and a burglary. So what we're looking for here is probability of A and B. Is that true? Now, what are we given? What probabilities are we given?
Probability of a property crime in the U.S. in a rural area over the whole U.S.
Okay, so we are given the rate of property crimes in rural areas. Is that the probability of A or the probability of B? Okay, so it says 5.1% are crimes in rural areas. So that's A, right? They're giving us that number. They're saying that if you randomly selected a crime in America, it would be there's a 5.1% chance you'd be looking at a property crime. Okay. Now, what's the other thing that's given to us here?
The percentage of property crimes that are burglaries in a rural area.
1.6% of all property crimes in the U.S. are burglaries in rural areas. So what is that?
Isn't it telling us that out of the 5.1, 1.6 of those are burglaries?
Ooh, is it?
Yeah.
That's why I improved that word.
Yeah, me too.
It's also what we can't see.
What?
Did you write this?
Isn't 1.6?
I think I copied it wrong. I thought I pulled it out of a practice problem, but now I'm thinking I wrote it down wrong. This doesn't make any damn sense.
It's asking us what percent of.
It says what percent of property crimes in rural areas are burglaries? What percent of property crimes in rural areas are burglaries? No, no, no. It's not. It's not actually. It's not. That I don't think that is what it's actually. I think we got the goal wrong. What percent of property crimes in rural areas are burglaries?
1.6?
No. That's in the whole U.S. If you look at every crime in all of the United States, 1.6% of them are burglaries in rural areas.
I think it's giving us enough to answer the question.
I think it is, but I think we misidentified the unknown value. Now this is saying what percent of property crimes in rural areas are burglaries. Where are we restricting ourselves to in that question?
Areas.
We're just interested in rural areas. I don't care about the population as a whole. So I'm telling you only within a rural area. So restrict yourself to that. So isn't that
31.4%.
maybe? How'd you get that?
I think the 1.6 divided by 5.1.
That could be the case, and I think it's going to end up being the case. Here's why. What am I basically doing here when I'm restricting you to rural areas, in terms of like what we talked about yesterday?
Using the 5.1 as your goal.
Because that's a what type of condition? Remember the one we did with the teachers, and we restricted ourselves to just people with master's degrees, and that was called a given condition, right? Here, what am I really saying? I'm forcing you to look at rural areas. So I'm saying that given that you're talking about property crimes in a rural area, right? Of property crimes in the rural area, so that's the given condition. Now I want to know what's the probability of burglaries. That's my question. What's the probability of a burglary given that you're only looking at rural areas? Yeah. And I think your answer is correct. And we're going to be able to see that because what is this 1.6%? It's the probability of what? Of all properties in the U.S., these are burglaries in rural areas. Isn't that? What is that? What goes right here? Is that just B? Is that the probability of just burglaries overall?
Oh no, it's A over or B over A or A over B, one or the other.
A and B.
I think it is. Isn't that exactly the Isn't that A and B? It's saying that if you look at the whole United States as a whole, 1.6% are burglaries in rural areas. Isn't that A and B? Rural area crimes that are also burglaries.
Oh yeah.
Yeah.
So is it like that little, when you make the two pies, it's the little section in between?
Yeah.
Okay.
Mhm.
That was it.
It's the intersection, yeah. This is the intersection. It's saying that the probability that you end up, so you're just randomly picking a crime file from all of the United States, 1.6% of them are burglaries in rural areas. That's A and B. This is our unknown condition. This is our unknown value, right? But we have a formula for that. I think I'm going to need an extra slide here. Yeah. Okay. Bring it back up. If I want to calculate the probability of B given A, the formula tells me that that should be what? The probability of what over the probability of what?
A and B.
Yeah, A and B, the intersection of the two on top. And what goes downstairs? Someone who said A, right? Why has it got to be A? Because A is the given condition, right? So the given the probability of the given condition is what goes downstairs. And we actually know these, right? So it was 0.016 in that were rural and burglaries. Downstairs, it was 0.05 something. 4? 1? Downstairs? That was just rural. And then, yeah, what does that proportion come out to be?
3-1.
Exactly 3-1?
3-7.
3-7?
No, yeah, 3-1, 3-7.
3-1, 3-7, so 3-1-4-ish. If we were going to go to 3 decimal places, that's pretty common. Yeah. Okay. So what does this mean? What's the actual interpretation of this? Sure. We just found out the answer.
So 31.4% property crimes
In rural areas. Yeah.
in rural areas are burglary.
Yes. Yeah, exactly. It's saying that's exactly what this means. It means that I'll say it a different way, but that's what it means. Within rural areas, 31.4% of property crimes are burglaries. So even though in terms of the entire nation, 5.1%, these crimes only constitute 5.1% of the overall crime rate in America. Within rural communities, burglaries constitute about a third of the crimes, property crimes. So, all right. Yes. So the key is correctly identify the unknown value. And then try to tease out, okay, so what do they actually give us? And the best way I find to do it is try to put it in probability statements. You know, did they give us the probability of A, or did they give us the probability of B, or what? Okay? That's our goal. All right. Any questions about that one? All right. Let's try something else. in the 110th Congress of the United States, 18.7% of the members were senators. And of those senators, 49% were Democrats. What is the probability that a randomly selected congressperson is both a senator and a Democrat? So you're just going to randomly select one person of Congress. And I want to know what's the probability you end up with a Democratic senator. All right. So, I would just, usually again, I give them letters. This one's not hard to say. Like D would be that you get a Democrat, and maybe S is that you get a senator. Okay. So, what's the unknown value here?
Senators, they're,
Give me a probability statement. Like P of what?
P of S/D
Slash is not an option.
for the straight line thing.
So is it probability of senator? Oh, I see. You were doing that. Given D, is that what we don't know, or is that what we're trying to find out?
S&D.
Oh, S&D.
Yeah.
Yeah.
I think what we're actually looking for here is senator and Democrat. Yeah. So sorry, slash is an option. I'm just not used to calling it that. I don't know. I guess I don't know what else you would call it.
Straight line thingy.
Straight line thingy. Is there a word? Is there a name for that symbol?
Probably.
Like the straight up and down line?
In Linux, it's called a pipe.
In Linux, it's called a pipe.
You pipe it, yeah.
It's true, in Linux it is called a pipe.
All right.
But even I call it straight line.
All right. Anything else? What else? Sorry. What else do we know? Sorry, I didn't even write it down. What's known? So there's two percentages there, so they must be somehow we could relate them to probabilities. I'm getting squished down here, so we'll just do one.
S is 18.7.
The probability of S, I agree, is 0.187 because 18.7% are senators. Okay.
And then D is 49%.
Is that the probability of D? Is that just the probability of being a Democrat overall?
S/D.
Is that D? Is it S given D?
When you just add the two together.
S and
Is it S and D? Is it D given S? What is it? What is 49%? S and D. Isn't that what we're trying to figure out?
That would be D of S, since it's 49% of the 18.7.
Is it? So I don't think it's this one. Because that one's what. That's what we're actually trying to look for, right? So, well, someone just said. I'm sorry. What did you
We'll
say?
go D of S since it's the 49% within the 18.7.
Is it D? You're saying D given S or S given D?
That's given D.
no, it's D given
What is D given S mean? Let's put it in words. D given S. What is D? Democrat given senator. What does S given D mean? Senator given Democrat. Which one are we given in this problem? Is that what we're given? Which one is it? I'm waiting for a consensus. Yeah. This is saying, yeah, senator given Democrat, that's like saying you're taking all the Democrats in Congress and you're telling me how many of them are senators, right? There's 2 chambers of Congress, yes?
Yeah.
Okay, we all know our civics. Okay. There's the House of Representatives and the senators, right? So there's plenty of people in Congress that are not senators. In fact, most people in Congress are not senators. The House of Representatives has 400 and some odd representatives in it or something, right?
Yeah.
430 something. There's only 100 senators. Never changes. Always 100. So anyways, so yeah, I agree with you. Senator given Democrat, that means you're just lumping all the Democrats together and now you're figuring out what percent of them are senators. But that, I don't think that's what we're given. This says of the senators. Yes. So I think it's this. This is the probability we're given. The probability of Democrat given that they're a senator. So that of the senators, that's telling us that senators is the given condition, and within that population, 49% are Democrats. Okay? Yes. So now let's erase all this madness and clean this up a little. Don't think it's that. And it wasn't this, we decided, because that would be a different thing. So I think what we are given, in fact, is this, the probability of Democrat given senator. Oh, I need more. No, I could just put it down here. There you go. So we know the probability of being a senator. We know the probability of being a Democrat given that you're a senator. Is it possible to figure out what the probability of being both a senator and a Democrat is? Is it possible? Yes? No? Maybe so? I think so. Come back to tree diagrams. Let's put another blank slide in here. Apparently I was planning on writing really small. Think about the formula for conditional probability. Right? Hang on. If I was looking at what is the probability, just formula-wise, what is P of D given S? Just by the formula, it would be what? Yeah, that would be just formulaically what the probability of Democrat given senator would be. Now, which of these values do we know? I know that. Don't we know this?
Right.
If I have an equation of 3 variables and I know 2 of them, can I solve for the third one?
Correct.
Hope so. So probability of Democrat given senator, that was that 0.49. Probability of D and S, that's what we don't know. But what we do know is the probability of being a senator overall is 0.187. So how do you solve for Democrat and senator at that point? You just multiply, yeah? Multiply. Yeah. And whatever that comes out to be,
0.092.
0.92?
Yeah.
So if you're just randomly picking up a congressperson out of either chamber of Congress, there's a 9.2% chance that the person you pick is going to be a Democrat and a senator. All right? Cool. Makes sense? Okay. This is actually this is another way we can use the conditional formula. Sometimes the conditional probability formula can actually be used to solve for probabilities of intersections. If you have a given probability and an outright probability, sometimes you can use this. The other way to solve these, and actually I'm a big fan of doing it this way. Some people really loathe every time I try to draw tree diagrams, but a tree diagram actually works really nicely. The way that tree diagrams can help us, for example, is so you go first. You make the split, and you look at, based on what we were given, we could look at which chamber of Congress they're in. So you have senators, and then you have their complement, non-senators, right? and it told us that 0.187 were senators, which would mean, I guess, how many would have to be non-senators? What would that be? 813 would have to be non-senators. So I guess if 18.7% are senators, then the other 81% would have to be House of Representatives. Yeah. Then from there, we're going to split, because within senators, you can have Democrats and non-Democrats. Just like in the other house, you could also have Democrats and non-Democrats. Okay. So it tells us in our problem that of these senators, 49% are Democrats, which apparently must mean that 51% are non-Democrats. And then what you look at is okay, so what branch of this tree are we interested in?
Top one.
Yeah, we want the branch that gives us senators that are also Democrats. This is the branch we want. And if you want to find the probability of a branch, you can just multiply across the probabilities of the branches that lead there. Yeah. So I just multiply this times this, and we get exactly what we got before. Okay? So tree diagrams can be pretty handy. Yeah. I like them. Less formulas.
Nice to have a visual too.
Mm-hmm.
Helps keep everything straight.
Yeah, I think so. All right. But if you can line it out like that, then you just multiply straight across, get where you want to be. That's the probability you pick. Okay. So let's say you got this is an example where a tree diagram would work really nicely, I think. So you got an undergraduate psychology class. It's got 40 students, and 23 of them are female. So let's say that when you're going to randomly select 2 students. How are you going to? What's the probability that you end up with a female first and a male second? What's that? Well, it's a little more complicated, I think, because first off, our students aren't equally split, right? So, what do you think? You can think of this as, we can try to do it formulaically and think about the probability of maybe a female first and a male second, and try to come up with some, I don't know, formulaic way to do this. I think there's a better way to do it though, and I think it's a tree diagram. So let's draw a diagram here. You got your first pick, right? And on your first pick, you could either pick a female or a male. And then you go in and you make your second pick. And on your second pick, you can pick either a female or a male. Right? So there's basically four options here. Right? You're gonna end up with 2 females, a female then a male, or a male and a female, or then 2 males in a row. All right. Now, what branch are we interested in landing on? Female first, male second. This is where we want to be. Now, the question though is, what probabilities belong on all these branches? So if you just think about your first pick, what's your probability of picking up a female on that first pick?
0.57.
Yeah, how you get that? Yeah, so there's 23 in the class out of 40 total, which means what's your probability of a male on that first pick? Yeah, 17 out of 40 or whatever decimal that comes out to be. I'll leave it as fractions, but we'll do decimal. We'll go to decimals at the end. I want to leave it as the numbers for a reason. Now, that's great. So now what happens though, what happens right here? So what's the probability of picking that male second?
17 out of 40 again.
See, now this is where the tree diagram helps because notice we've actually picked somebody already. Yeah? So we don't have 40 students to pick from anymore. We only have 39. Because what's actually the probability of a female on your next pick? Yeah, there's only 22 females left because I already picked one up. And there's now 39 students left, right? So there's one less female, one less student, but the same number of males if you picked a female first. On the other hand, though, if you would have picked a male first, what would have been the probability of a female? You would have still had all 23 out of the 39 remaining females, but you would have only had 16 males to pick from out of the 39 remaining students, right? So the first event actually affects your probabilities on your second event. Of course, so now we know this is the branch we want to be on, so then we can just take those probabilities, 23 out of 40 times 17 out of 39, boom, and we can get whatever that approximates out to. What do you get for that?
0.2506 or 25.1.
So 0.251 if you round it. Anybody else get that? 23 divided by 40 times 17 divided by 39. Any other takers? 0.251 if you round it to then 3. Yeah, 1. Cool. There you go. All right. Yeah.
So you showed that the top one was the one that you wanted to go with, and it was because that was the one that had the females first, right? So did you just know that because you chose to put your probability things there, like the 22 over 39 and 17 out of 39?
You mean how I can actually construct my tree, or how I
Yeah,
knew
you
which
did that
branch?
by just taking away like one female rather than taking away
Yeah.
one male, right?
Right.
Okay.
Yeah. I mean, you can arrange your tree in other ways. Like, yeah, it could be males on top of females on. I mean, it doesn't really matter. Just as long as you're consistent, so that in the next round, if you picked a male before, the male number needs to go down. If you picked a female before, the female number needs to go down, and the total also has to go down on every single step. Yeah. All right. Cool. So I like tree diagrams. I think they're fun. They get kind of messy though. You don't want to be drawing like tree diagrams with like, I don't know, 105 branches or something, but it is. All right. We already did this one, didn't we?
Yeah.
Oh yeah. I don't know why I said we're going to revisit that one.
Maybe to do it as a tree diagram instead of,
I don't know either. Moving on. Oh, okay, yeah, but it was good to revisit because if you remember the implication, what was the implication on this one when we went back and did this one? You don't have to rewrite it down, but what was the implication? Right? Yeah, given a master's, field trip was more likely. That was the implication. And the last one, if in the last example with a tree diagram, if I pick a female first, does it affect my probability of getting a male second? If I know what my first pick was, does it change my probability of a male on the second pick? A little bit, doesn't it? Because if a female came first, I got 17 out of 39. If a male came first, I only have 16 out of 39. So I give you some information, and it changes the probability of the next event. Here, I gave you some information about their degree status. It changes the probability of them taking their students on a field trip. We did the example with the extra credit points, right? I gave you some information about the numbers on the dice. It changes your probability of winning the game, right? So this is getting at a concept of independence versus dependence. So we say that two events are independent if knowing the outcome of one has no effect on the probability of the other. I don't know how to spell occurring. I want to say there's 2 C's and maybe only 1 R, but I don't really know. There might be 2 R's in there. Okay. So if I give you information and it doesn't change the probability, then that would be independent events. All the examples I just gave you are actually what we call dependent, because by giving you information about one thing, it changes the probability of the other. It's not independent. There is a probability definition. Okay. So an alternate way to define this. So what we're really saying here is that if you tell me that if you give me the probability of A given B, so you give me a condition like B happened or B definitely is going to happen, and it doesn't actually change the probability of A at all, then that tells you that they're independents. So this is the definition of independence we can use to check for independence. This is the intuitive meaning of independence. Okay. So sort of the wordsy interpretation and then the mathematical way that we actually check for independence. Is the conditional probability the same as just the probability overall? Right. If I tell you something about the dice and it doesn't change your probability of winning, then it was useless information. It didn't help you at all. That's independence. All right. So this is what we're going to actually use to check it. All right. So let's go back to the dice, for example. All right. Let's say that I want to know what I have a couple events in mind. So either that the sum is less than 7, the sum is even, or the sum is odd. And so my question is are the events A and B independent? In other words, let's say that you're going to bet on this, right? Let's say that you're going to bet on the sum being less than 7. And I roll the dice over here, and then I look at it and I say, oh, hey, just so you know, the dice turned up even. Does that actually change the odds of what you bet on occurring? That's what I want to know. Does it? Okay.
Well, 7 isn't an even number, so.
It was asking for the sum less than 7, so 6.
Oh,
or
I read it wrong then. Just
2.
kidding.
I read the same way you did.
Yeah, I read it that it was
Then
7.
it was.
Yeah, not that it is 7.
Less than 7. Oh, then no, because you could still have an even number and it'd be less than 7.
Yeah, so think about this. These were all our outcomes. Oh, there's a 2. 3. These are all the ones I don't really even need to fill in the West. We don't really care about it. So what's the overall probability of A? Well, just without B or C occurring at all. Like, I'm not worried about B or C at all. What's the probability, if I don't give you any information and I'm asking, hey, you want to take this bet? What's the probability that you roll the 2 dice and the sum actually comes up less than 7?
15 over 30.
Yeah, so you look at all of these outcomes, right? Yeah? Okay. Then that's how many did we decide? Is it 15?
Yeah.
Yeah. So there's 15 ways to do it out of 36, which would reduce to maybe 5/12, which is as a decimal what? 0.4 what? I heard it first one.
0.416.
416? 416?
7.
417 if you round it. Yeah, well, From now on, let's just all round all our probabilities to 3 decimals. Okay, that's the most common, because then if you convert it to percentages, it gives you 1 decimal beyond the percent. So, so this is the overall probability of rolling a number less than 7. That's pretty good odds, actually, right? Now, what I want to know is, what if I tell you, though, what if I give you this condition here? The sum is even, right? So what's the probability of A given B? Okay, so you're looking at the even ones, right? So there's 1, 2, 3, 4, 5, 6, 7, 8. There's 9 ways to do that, right? So there's 9. But yeah, how many do you have to pick from? If I tell you that the sum is even, then how many options are there for those dice? There's only 18. Remember, if I tell you that there's only 8, if I tell you that the sum has to be even, then there's only 18 possible ways that die can land. Those 2 dice can land, because all of the odd numbers are out of the question. We threw them out, right? So there's 9 ways to do it out of 18. So what's your probability of winning now? 50%. Right? Yeah, question.
Is it 8? Why is it 18? Is it like 18 in total even?
It's because remember, we're given that it has to be an even number. So I can talk. So if you look over at this chart, so if I fill it all the way in, before I gave you any conditions, there was 36 ways that those 2 dice could land. But if I tell you that it landed on an even number, I just knocked out all of these odd options. Can't be a 3, can't be a 5, can't be a 7, can't be a 9, can't be 11. Those 18 possibilities are out. So only the evens are left.
I thought it was out of the 7 and lower.
Yeah, so that's out now. We don't have to just pay attention to the ones that are less than 7.
Well, that's not the given condition, though.
So now it's just that it's even out of the entire rolls of. How do you know how much to roll?
Okay, so remember, our primary interest is the same thing. We still want to roll a number less than 7. Like, that's still our goal, right? But what we've done is, with the given condition, I've changed the population. So now I told you is even. So I knocked out a huge chunk of possibilities. These are now our only possible answers, right? And where are the ones that are less than 7?
Just from 6.
Yeah. So now, if you look at the possibilities, there's only 18 possible down here, right? Count up the numbers. There's only 18 possibilities. And how many of them are less than 7? 1, 2.
I get what you're saying.
Yeah, 9. Yeah. So, are these events independent? By definition? No. So the probability of A does not equal the probability of A given B, so they are not independent. No. Another way we would say that is they are dependent. If I tell you that the sum is even, it actually makes your odds better. It makes the bet a better bet. Okay? All right, makes sense? Cool. We're out of time. So, get started on the homework. Go roll some dice. And I will see you back on Monday. Yeah, you can go ahead and just lay your tests up here on your way out if you have corrections. If you didn't staple them, just make sure you get your name on all the pages and just lay them one on top of the other. I'll staple them back in my office.